I guess you should see my slides now.
Yes, yes. And then it's a great pleasure to introduce our next speaker, Dan Kral from Masaryk University, who will speak on parameterized approach to block structured integer programs. Please, Dan.
Thank you, Fedor, for the introduction. I am sorry I couldn't come to Bonn, but still I am hopeful that there could be some remote collaboration, in particular, like if you find some topics that I mentioned today interesting and you would like to talk a little bit more or explain me some things that I might not be just aware in the area of integer programming, I will be very happy to hear. And I hope that despite the distance, like can be some collaboration going on. And I'm also happy to mention that some of my co-authors are actually right now listening and are also eager to participate in such collaboration. So as I mentioned in the morning, by training, I'm more on the graph theory side. And the story started with a colleague of mine from Prague showed up once in my office and asked me a question about integer programming. And this is how this work originated. And I should mention this is also a joint work with various people, and I will mention them during the lecture. Oops. Yeah. So I think I don't have to introduce integer programming too much for this audience. Just to be sure, we're trying to minimize some separable convex function subject to some linear constraints, having some lower and upper bounds on the individual variables, and the most important condition is that we actually want the solution to be integral. And this problem is, of course, well known to be NP hard. It actually appears among the 21 first NP complete problems established by Karp. And as we already had in the morning, it's well known to be tractable for the fixed dimensions. And there have been various extensions. I put here some buzzwords. And in the spirit, essentially, we can, or at least it was in the past, that we can solve instances that are of some kind of special form. And the point of this work is a result due to Kotetzky on and oh my gosh, Kotetzky, Levin, and on. And I will state that result in a second. So for that, I will need a definition from graph theory, and that's a definition of tree depth. I think some of you might have heard of another parameter called tree width, which is maybe more well known, but it also is less restrictive, and actually this parameter is not so relevant in relation to integer programming. So let me introduce this graph parameter in case you haven't seen it earlier. And for that, I will first need and I should mention, of course, feel free to interrupt at any time with questions. I have also opened a chat on the side. So in case if you're a remote participant and you have a question, just write it in the chat and I try to be organized to notice. So I have a tree. And the closure of the tree, so it's a rooted tree. So maybe it's the black tree that is shown at the bottom of this slide. And I assume you can see my mouse. And when I add all the edges between vertices and its descendants. So for example, the root will be joined to all the vertices, while this vertex, this leaf will be joined only to the 3 vertices on the path to the root. And when the tree depth of a graph, of a connected graph, is the minimum depth of a tree that its closure contains the graph. So in particular, any subgraph of this graph with black and blue edges would have tree depth at most 4. And it's not hard to show that tree depth is an upper bound on path width and tree width, which are maybe two better known graph width parameters. And but I don't want to define either of them right now, and just the tree depth will be the parameter important for the rest. I should also mention that there is an equivalent definition through so-called centered colorings, which are actually important in relation to sparsity in graphs. But again, something that I don't have time to go into the detail, but I just wanted to mention the connection. And perhaps the most or one of the most basic facts, which is also I think nice to remember is that the graph has a large tree depth if and only if it has a long path in one direction. Namely, if it doesn't have a long path, it has a small tree depth, it's rather easy to see because one just performs the depth first search, and the depth first search, the closure of the depth first search will actually contain the graph. In the other direction, it's requires showing that the presence of a long path implies a lower bound on the tree depth, which is also not a difficult proof. And but I don't want to spend time on it. So the relation of tree depth to integer programming was explored by Kotetzky, Levin, and on. It's rather a recent result, and for that I will still need one more definition. So I have a matrix A, and this is the matrix A which appears in the instances describing an integer program. And I may define so-called primal and dual graphs. So let me start with the primal graph. So a primal graph is a graph whose vertices are the columns of the matrix, and two vertices are adjacent if and only if the corresponding columns contain the non-zero entries in the same row. And so this will be the primal graph, and the primal tree depth of the matrix is just the tree depth of this column graph of the matrix. And Kotetzky, Levin, and on show that integer programming is fifth parameter tractable when parameterized by the primal tree depth of the matrix, of the instance matrix, and the entry complexity. And we also established a kind of a dual result, that instead of taking the graph on the columns, one may take the graphs on the rows and put an edge between two rows if and only if as a column such that in that column the two rows have non-zero entries. And again, integer programming is fixed parameter tractable when parameterized by the dual tree depth and the entry complexity. So these results in particular include some of the tractability results I mentioned really briefly on the first slide. But there's an obvious problem with, or not maybe a problem, but an obvious limit of these results. And that while when we give it in an instance, we can check that its primal or dual tree depth is small, but it still may happen that that instance is equivalent to an instance with a primal, with a small primal tree depth or a small dual tree depth, and we just might not be aware of it. So for example, here I put a matrix that is row equivalent, and therefore the integer program given by this constraint matrix should have the same complexity to this matrix, and this matrix has a very low dual tree depth, namely 3, because the graph, and actually let me try to draw the graph. I will try to be brave. So if I am looking at this at this primal graph, so can you see what I'm drawing?
Yes.
Very good. So I will have vertices for the columns, and an edge will be if there's a non-zero entry in two of these columns. So this will be the primal graph, and its tree depth is actually 3. While the tree depth of the primal graph of this matrix is 5, because it's just the complete graph on 5 vertices. So the natural question is, given a matrix A, whether there is a row equivalent matrix with a small primal or dual tree depth. So let's remind me that the graphs I just drawn here, these are the graphs corresponding, these are the primal graphs on the columns, and I'm putting an edge if two columns have non-zero entry in the same row. And of course, one can ask a similar question in the dual setting, where I'm putting vertices for the rows and putting an edge if two rows have a non-zero entry, both rows have non-zero entry in the same column. So this is the question which Martin approached me with, and he asked me if I maybe know something that actually could characterize when a given matrix has a small primal, or is equivalent to a matrix with a small primal or a small dual tree depth. And these are the results that I wish to talk in the next 15 minutes about. So for that, I will actually need to introduce some definitions, and namely, like we approach this problem with the tools from the MATROID theory. I am sure many many people in the audience know what a matroid is, but still I would like to very briefly go through some of the definitions that the talk is self-contained. So a matroid is a pair of a base set and a distinguished subset of elements of the base set, which will be referred to as independent sets. And one can think of, and I think it's actually for most of the, or almost everything that will be in this talk, I will be working mostly with the so-called vectors matroids, where the elements of the ground set will be vectors, and the independent sets will be linear independent sets of vectors. So for a general notion of the matroid, I want the set of independent sets to be hereditary, meaning that if a set is independent and the subset is independent, and I want an augmentation axiom to be satisfied, which means that if I have two independent sets, one is smaller than the other, I can find an element in the larger that I can add to the smaller, and the set will be independent. And I said a particular example of a matroid is a set of vectors over some field, which may be finite or infinite, and independent sets being sets of linear independent subsets of vectors. And it's not hard to see that clearly they're hereditary, and the augmentation axiom is also rather easy to establish. And I will be saying that a matroid is representable over a particular field if it's isomorphic to a vector matroid over that field, meaning I have an isomorphism between the elements that possess the independent set. And sometimes I will be also talking about F-represented matroids, which I would like to emphasize that it's not only representable, but I'm actually given the matroid by a particular representation over a field F. So here I put some examples. So for example, the Fano plane, which is a matroid that can be viewed actually, a Fano plane, which is actually a design, but can be viewed as a matroid with 7 elements represented over GF2 with this particular representation. And it's an example of a matroid that is representable over some field, namely the binary field, but it's actually not representable over the 3-element field. And I will need 3 more definitions. So I think 2 of them are rather well known. So the first one is the notion of a rank of a set, which is just the maximum size of an independent subset of a set. It can be shown that all maximal independent subsets of the set have the same cardinality. And in case of representable matroids, the rank of a set is just the dimension of the subspace generated by the elements of that set. When circuit is a minimal dependent set, in the case of Fano plane, circuits are precisely the lines of the Fano plane. And then I will need one definition, which is maybe less well known, and it's the definition of connectivity of a matroid. And a matroid is connected if every 2 elements are in a common circuit. So it can be shown that if one has a matroid, then being in a common circuit is a binary relation that is transitive. And when the equivalence classes of this relation, like symmetry and reflexivity, is rather easy, are actually connectivity components of a matroid. And just to finish the introduction to matroids, one particular example or another important class of matroids are so-called graphic matroids, which can be obtained by a graph by associating by the element set of the matroid being the edges of the graph and the independent sets being acyclic subsets. So I put here an example, which actually should also convince you that every graphic matroid is representable over any field. So if this is my graph, so which has 4 vertices, 1, 2, 3, 4, when I will create a matrix, so the columns of this matrix will correspond to the edges, rows correspond to the vertices, and I put 1 and -1. So for example, the first, this column correspond to the edge between 1 and 4, and one can easily verify that these edges, these columns are in 1-to-1 correspondence with the edges of the graph, and the edges of the graph form an acyclic subset if and only if the corresponding columns of the matrix are linearly independent. So I wanted to mention graphic matroids because I think they form an important class of MATROIDs, in particular in relation to greedy algorithms, and I think it's also good to mention. And one thing, in addition to this, why I wanted to mention them is that I wanted to say that a graphic MATROID is connected if and only if the corresponding graph is two-vertex connected. So it doesn't make sense to actually talk about connected graphs, because if I take a tree, then the associated MATROID has let's say I take an n-vertex tree, the associated MATROID has n-1 elements which are independent, so it's completely disconnected. So the connectivity kind of starts being interested only when one starts looking at two-vertex connected graphs, and they correspond to, or where graphic MATROIDs are actually connected. So now I can start getting to the results. And as I said, like what we were looking at how the minimal primal or the minimal dual 3-depth of a matrix that is row equivalent to a given metric is demonstrated. And in both settings, it turned out that this demonstration goes through the MATROID, through the column MATROID of that matrix. So in the primal setting, we need a parameter which is called deletion depth, and it's recursively defined as put on this slide. So the deletion depth of a MATROID, if the MATROID has a single element, it's 1. So it's kind of the boundary condition. If I have a MATROID that is not connected, then it's the maximum depth of a component of that MATROID. And otherwise, I'm trying to delete an element, therefore the name deletion depth, in a way that the MATROID becomes disconnected, and when I recurse to the connectivity component. So it's 1 plus the minimum deletion depth of a MATROID obtained. And I do apologize, this shouldn't be contraction, this should be deletion deletion of an element. So I'm going through all the elements of the MATROID, trying to delete them, and look what is the deletion depth of the resulting MATROID, and taking the minimum of it. So it can be shown that computing the deletion depth of even an F-represented MATROID, even over a finite field, is NP complete. And on the other hand, when I parameterize by the deletion depth, and I have a finite field, when the analog of Kurzweil's theorem in the MATROID setting, which was proven by Hliněný about 20 years ago, shows that computing deletion depth is parameter tractable when parameterized by a finite field and the depth. So in the setting that we're interested in, we're looking at what we can say about the minimum primal 3-depth of a matrix that is row equivalent to a given matrix. So I should mention that this is a joint work with Marcin Briansky, who's a PhD student in Krakow, Kristina Pekárková, who's a PhD student in Brno, and Felix Schroeder, who's a PhD student at TU Berlin, and Martin Koutecký, who's a faculty in Prague, and who actually kind of initiated this project by suggesting that we should have a look using combinatorial tools at these width parameters. So we're looking at the minimum possible primal 3-depth of a matrix that is row equivalent to the matrix A, and it's actually this is the rather easy, even if it requires a small argument, to show that this minimum primal 3-depth is equal to the deletion depth. However, what is much harder is to actually complement it with a fixed parameter algorithm that will be useful for integer programming. Because for integer programming, we not only care about having a matrix with a small primal 3-depth, but we also need to be able to say something about the entry complexity. And it is well known that some matrices are row equivalent to matrices with a small primal 3-depth, but however, this comes at the expense of the entry complexity, which then makes it infeasible to actually apply the algorithms for integer programming, or this Koutecký-Levin-on framework. So what we actually did is we designed a fixed parameter algorithm which is parameterized by D and E, and it either outputs that the given matrix is not equivalent to a matrix with a small primal 3-depth and bounded entry complexity, or if find a matrix with a small primal 3-depth and the entry complexity bounded by a function of D and E. So unfortunately, we don't know how to put here the same E as here, but from the at least from the fixed parameter point of view, we kind of morally know that the integer programming is fixed parameter tractable when parameterized by the primal 3-depth, by the minimum primal 3-depth, in the sense that if we can not avoid this blow up in the entry complexity, when there's nothing what one can do about it, but if we can avoid it when we find a matrix still with entry complexity bounded. So the situation is actually much more complex in the dual setting when one is looking at minimizing the dual 3-depth. And for that, I will need a definition which perhaps is more complex than the one of the deletion depth. And I prepare here the definition for matroids which are not in general representable over a finite field or over any field. And then on the next slide, I will mention an equivalent definition for matroids representable over fields.
Daniel?
Yes.
So just to clear out some confusion in my head. So, I mean, all of this tree depth stuff and entry complexity stuff is usually to bound the complexity of like the Graver basis, right? To some extent.
Yes, yes. So it's.
But isn't that independent of the representation?
I have the last slide which somehow relates to this. So you completely right that that one can be looking at the parameterization about with what one can say about Graver basis, and so let me get to that on the last slide that I have prepared. And you completely right that this is actually might be the parameterization that one might be more interested in, and but still let me go through this. And from my combinatorial point of view, I may be more interested in characterization in terms of this primal and dual 3-depth. But you're completely right that one should also think about like what are the limits in terms of the parameterization in terms of the complexity of Graver basis. And let me get to that at the end of the talk.
Thanks.
Yeah. Thanks for the question. So let me maybe. Okay, I think I might be running out of time. So let me actually go to the equivalent definition of branch depth. And this is the equivalent definition for represented matroids. So if the matroid has rank 1, its branch depth is 1. If it's disconnected, it's the maximum depth of a component. And otherwise, what one is trying to do, one is trying to factor by a one-dimensional space. So we have a notion of factoring in linear spaces. And if one has a represented matroid, it makes sense to factor over one-dimensional spaces. So by factoring over one-dimensional space, in principle, the matroid may become disconnected. So one is trying to find a space such that if one factors by it, when the chances of splitting the matroid into simple components are as large as possible. And there are a couple of facts that the branch depth of a graphic matroid is at most the 3-depth of the graph, which perhaps one would like to have, because if one wants to think of the analog of a 3-depth, and maybe it should be somehow related to the matroids. The branch width, which is the 3-width analog for matroids, is bounded by the branch depth. So similarly to the relation of 3-width and 3-depth in graphs, we have again a more restrictive parameter here. And a matroid has a large branch depth if and only if it has a long circuit. So it doesn't make sense to speak about paths, rather circuits are what keeps matroids connected. And again, we have similarly as in the setting of graphs where the large 3-depth was equivalent to having a long path. Here we have a large branch depth equivalent to having a long circuit. And the result, which I proved together with my student, Timothy Chan, I should mention here that this is not the Timothy Chan from Urbana-Champaign, Jay Cooper, another student of mine, Martin Kotecký, who I have mentioned already, and Kristina Pekarková, also a PhD student of mine. So we showed that the minimum dual 3-depth is of a row equivalent matrix to a given matrix A is actually equal to the branch depth of the column matroid of the matrix A. And we managed to do much more here. We managed to to design a fixed parameter algorithm, which is parametrized by D and E, such that if I get a matrix A with bounded entry complexity, when the algorithm either says that there is no matrix with a small dual tree depth, meaning the dual tree depth at most D, or finds a matrix that has a small dual tree depth, it's a row equivalent to the original one, and the entry complexity of that matrix is bounded by the function of D and the entry complexity of the original matrix. So here, like the outcome is that if the original matrix has a small entry complexity, then we know that that if there is a row equivalent matrix with a small dual tree depth, there's also one with the small entry complexity. So this implies that the integer programming is fixed parameter tractable when parameterized by dual tree depth and the entry complexity. So I prepared one slide which I originally wanted to skip, but since I get a question which actually I think is somewhat morally answered on this slide, so let me go through this slide very briefly. And so I have a constraint matrix, and I want to define a circuit of that constraint matrix, which is the supervised minimal integer vector in the kernel with all entries comprime. And when there are various ways how one can define the complexity of the circuits of a matrix, one may use different norms. One of the norms one may use is L1 norm. So I will be writing C1A for the maximum L1 norm of a circuit of a matrix. And this is indeed invariant. And I think this actually goes in the direction of the question that I got from the audience, because and now I must say that as I'm more on the combinatorial side, I'm not such an expert in the integer programming, even if I'm trying to learn. I do understand that this complexity is actually related to the complexity of Graver bases. And the natural question is whether integer programming is fixed parameter tractable when parameterized by this C1 complexity. And we can actually answer this question positively, because what's possible to show is that the branch depth of the column matroid of the matrix A, which, as we know from the previous slide, is the smallest possible dual tree depth, is actually bounded by C1 cubed. And when thus applying the results or the machinery that is behind our results, we can show that if the C1 complexity of a matrix is bounded, when there exists a row equivalent matrix with a small dual tree depth and entry complexity just bounded by the function of K. And to this we can apply the Kotetzky-Levin on framework, and therefore, for this matrix, the instance can be solved using their algorithm. So I think I not only ran out of time, I actually went over the time. So I think it's time to thank you for your attention. I'm very happy to take questions, and I will be even more eager to actually set up some Zoom meetings later with either on-site or remote participants to discuss the topics that I have just presented, both to learn new things and maybe even prove new things.
Thank you very much, Kral.